Hello everyone. Once again welcome to my YouTube channel Physics with Dr. Sanjay Bhargava. Hope you are enjoying my videos on microwave electronics. In this video we are going to discuss about cylindrical cavity resonator. We'll calculate its resonate frequency and wavelength both for TM and TE modes. So let us talk about cylindrical cavity resonator. A cylindrical cavity resonator is a section of circular waveguide shorted at both the ends by conducting plates placed normal to the axis of the cylinder. So we had cylindrical waveguide. The two opposite ends, that is the circular cross sections, were open in circular waveguide. Now if both those circular cross sections are shorted with metallic walls, then it would generate an closed volume which can be termed as cylindrical cavity resonator. So we have defined cylindrical cavity resonator as a section of circular waveguide which is shorted at both the ends by conducting plates which have been placed normal to the axis of the cylinder. तो प्लेट्स को हमने कैसे रखा है? एक्सिस के परपेंडिकुलर रखा है ताकि हमारा सर्कुलर वेवगाइड हमारे लिए सर्कुलर कैविटी रेजोनेटर में कन्वर्ट हो जाए. द कंडक्टिंग वॉल्स और द प्लेट्स रिफ्लेक्ट द इलेक्ट्रोमैग्नेटिक वेव्स which result in the formation of stationary waves in the z direction in addition to the normal circular waveguide field pattern. So, बिल्कुल जैसा हम रेक्टेंगुलर कैविटी रेजोनेटर में बोलते थे कि वहां पर x और y डायरेक्शन के फील्ड कन्फिगुरेशंस अनचेंज्ड रहेंगे, वेवगाइड की तरह ही मिलेंगे, केवल z डायरेक्शन में एक नया फील्ड स्टैंडिंग वेव पैटर्न जनरेट होगा. उसी तरीके से यहां पर भी केवल जो z डायरेक्शन है उसमें आपको एडिशनल वेव स्टैंडिंग वेव्स पैटर्न मिल जाएंगे, पर बाकी जो डायरेक्शंस थे उन सब में वही जो सर्कुलर वेवगाइड के फील्ड पैटर्न्स थे वैसे ही फील्ड पैटर्न आपको देखने के लिए मिलेंगे. दिस रिप्रेजेंट्स फिगर द फील्ड कॉन्फ़िगरेशन फॉर वेरियस मोड्स. L is equal to 1, that is a single loop. L is equal to 2, we are finding the two loops. These two are the two shorted ends at z is equal to 0 and z is equal to c. Now here this represents the axis. A is the radius of the circular waveguide, phi is the azimuthal angle, and this shows TE waves where Ez would be equal to 0. Now we need to calculate what are the field equations for TE waves in a cylindrical cavity resonator. So the TE waves in the cylindrical waveguide are once again the earlier equations only which have been already derived by us in our earlier videos. So Hz is given as Cn Jn h rho cos n phi e power minus gamma z. H rho is minus gamma upon h Cn Jn dash h rho cos n phi e power minus gamma z. H phi would be gamma upon rho h square n Cn Jn h rho sin n phi e power minus gamma z. Similarly, the electric field equations are also the same as we had discussed in our earlier videos for the cylindrical waveguide. E rho would be equal to j omega mu upon rho h square n Cn Jn h rho sin n phi e power minus gamma z. What is Jn h rho? That is Bessel's function of first kind. Omega, this can be put equal to omega mu upon beta h phi, can also be written as minus j omega mu upon rho h square delta z hz by delta phi. Similarly, E phi is written as j omega mu upon h Cn Jn dash h rho cos n phi e power minus gamma z, can also be written as minus omega mu upon beta h rho. So Jn dash, that means the first derivative of the Bessel function. the propagating fields are reflected from the shorting placed at z is equal to 0 and z is equal to d, which result in standing waves in the z direction. A standing wave of axial magnetic field Hz is found by combining the forward and backward propagating TE waves. So Hz will be given by Jn h rho cos n phi Cn e power minus beta z plus Cn dash e power j beta z. Hz would be equal to 0 at z is equal to 0 according to the boundary condition. So you have to solve for Hz under the boundary condition which says Hz would be equal to 0 at z is equal to 0. So put as Hz is equal to 0, so we will find Cn plus Cn dash is equal to 0. So Cn would be equal to minus of Cn dash. So Hz would be now equal to Jn h rho cos n phi, Cn को अब हमने कॉमन ले लिया, e power minus j beta z minus of e power j beta z. And remember, sin beta z also we have already written as e power j beta z minus of e power minus j beta z upon 2j. So that helps me in writing the equation for Hz as minus 2j Cn Jn h rho cos n phi sin beta z. So we have determined the equation for Hz. Now Hz is also 0 at z is equal to d. So put Hz is equal to 0 at z is equal to d. So what we get is sine of a beta d would be equal to 0. So it would be equal to sine of p pi. So beta d can be put equal to p pi. So beta would be equal to p pi upon d, which would be equal to kz. P is an integer, can take the value 0, 1, 2 and 3. Thus for TENMP modes, Hz is equal to minus 2j Cn Jn h rho cos n phi sin beta z. So we have the equation for TENMP mode. The other components can be similarly obtained and obtained as h rho would be equal to minus 2j Cn n beta upon h, Jn dash h rho sin n phi cos beta z. H phi we will obtain as 2j Cn n beta upon rho h square, Jn h rho sin n phi cos beta z. Similarly, the electric field components would be E rho equals j omega r omega mu Cn upon rho h square Jn h rho sin n phi sin beta z. E phi is equal to j omega r mu Cn upon h Jn dash h rho cos n phi sin beta z. Already Ez is equal to 0 for TE modes. The electric and magnetic fields are in time phase quadrature, pi by 2 in exponent for h rho and h phi and not for e rho and e phi. The magnetic fields is plus minus pi by 2 out of phase relative to the electric field, right? So you can just see electric field means we have sin beta and here we have cos beta. They differ by an angle of plus minus pi by 2. That is what we are saying in the terms of language, that magnetic field is plus minus pi by 2 out of phase relative to the electric field. Now let us talk about TM waves. For TM waves, the basic requirement is Hz must be equal to 0. What does boundary condition require? Boundary condition requires E rho and E phi must vanish at z is equal to 0 and z is equal to d. So E rho and E phi must vanish. This gives Jn Ha is equal to 0 and Hz is equal to 0. The TM modes in the cylindrical waveguides are Ez would be An Jn h rho cos n phi e power minus gamma z. ये वही इक्वेशन है जो हमें पहले से मालूम है सिलेंड्रिकल वेवगाइड के अंदर. H rho would be given by j minus j omega r epsilon upon rho h square an and jn h rho sin n phi e power minus gamma z. H phi would be minus j omega r of epsilon upon h an jn dash h rho cos n phi e power minus gamma z. E rho can be written as minus gamma upon h an jn dash h rho cos n phi e power minus gamma z is equal to beta upon omega epsilon h phi. Similarly, E phi can be written as rho gamma upon rho h square an n jn h rho sin n phi e power minus gamma z can be written as minus beta upon omega epsilon h rho. For Tm NMP modes, the field components are now written as an jn h rho cos n phi cos beta z. E rho can be written as minus j beta an jn dash h rho cos n phi sin beta z upon h. E phi can be written as j beta n an upon h square jn h rho sin n phi sin beta z, and h rho is equal to minus j omega r epsilon n an jn h rho sin n phi cos beta z, where beta is nothing but p pi upon d. P is an integer 0, 1, 2, 3, any value possible. H phi is minus j omega r epsilon upon h an jn dash h rho cos n phi cos beta z. N is equal to 0, 1, 2, 3 is the number of half periodicity in phi. M is number of zeros in the field in a radial direction, and P gives number of halfway variation in z direction. Now, after knowing the field components, we are in a position to calculate the resonance frequency and the wavelength. The resonance frequency is determined by the propagation constant. And how do we define propagation constant? Gamma is equal to j beta, which can be written as under root of h square minus omega r ka square mu epsilon. Omega r is supposed to be the resonance frequency. So omega r is 1 upon mu epsilon under root of h square plus beta square. For TE NMP modes, Fr would be given by 1 upon 2 pi under root mu epsilon h dash nm upon a ka square plus p pi upon d ka whole square. While for TM NMP modes, the resonance frequency is given by 1 upon 2 pi under root mu epsilon under root of h nm upon a ka square plus p pi upon d ka whole square. H dash nm is the mth root of j and dash ha is equal to 0, while hnm is the mth root of j and ha is equal to 0. In general, h nm and h dash nm are not equal. So, cylindrical resonators do not possess degenerate modes as possessed by rectangular or cubical resonators when a is equal to b or a is equal to b is equal to c. तो रेक्टेंगुलर कैविटी रेजोनेटर और क्यूबिकल रेजोनेटर में डीजेनरेट मोड्स होते थे, पर यहाँ पर चूंकि HNM और H-NM का वैल्यू कभी बराबर नहीं होता, इसीलिए यहाँ पर डीजेनरेट मोड्स नहीं होते हैं सिलेंड्रिकल कैविटी रेजोनेटर में. हाँ, अब मैं उम्मीद करता हूं कि आपको सिलेंड्रिकल कैविटी रेजोनेटर के फील्ड मोड्स का कैलकुलेशन, फिर रेजोनेट फ्रीक्वेंसी, रेजोनेट वेवलेंथ को डिराइव करना अच्छे से समझ में आ गया होगा. अगर आपको हमारे वीडियोस अच्छे लगते हैं तो मेरा रिक्वेस्ट है उनको लाइक करिए, कमेंट करिए, चैनल को सब्सक्राइब करिए, बेल आइकन बटन को आप कहीं ना कहीं पर प्रेस करिए ताकि नए आने वाले वीडियोस के नोटिफिकेशन आपको सही टाइम पर मिल पाएं. Thank you and thank you.